Let's use some algebra tiles to remember the basics of completing the square. In this polynomial, x squared is represented by an x by x block. 4x is represented by 4 blocks that are x by 1. And 3 is represented by 3 unit blocks that are 1 by 1. We want to rearrange the blocks so that they form a perfect square. We'll start by looking at the 4 blocks that are x by 1. We'd like to rearrange them so that we have the same number of blocks on each side of the square. So if we take the 4 blocks and divide them into 2 equal groups, we have 2 of those blocks on each side. That means that the square that we're trying to form measures x plus 2 by x plus 2. And the area of that square would be x plus 2 quantity squared. But down in the lower right portion of that red square, you'll see that we have some area missing that we need to fill up. We can do that by using our 3 unit blocks and filling in whatever area we can. So while the area of the red square is x plus 2 quantity squared, the area represented by our original polynomial is actually 1 unit block less than that. So, to write a polynomial that's equivalent to our original trinomial, we have to subtract 1 from the x plus 2 quantity squared. That's what's called completing the square. Now let's look at an extension to completing the square when we have a coefficient on our squared term that's not a 1. That means we have 2 x by x squares represented in our polynomial. It also means that we're not just completing 1 square, we're completing 2 squares. The linear coefficient's 8, so we have to take the 8 blocks that are x by 1 and rearrange them so that we have equal numbers of blocks on each side of our 2 squares. The constant term of 6 means we have 6 unit blocks to use to try to fill up the 2 red squares. The area of each red square is x plus 2 quantity squared, and we have 2 of them. We'll distribute the 6 unit blocks equally to each of the red squares. We've used all of the algebra tiles from our original polynomial to complete the squares, but you can also see that we're missing 1 unit square in each of the 2 squares. So the area of the original polynomial is actually 2 units less than the area of the 2 squares we've completed. Let's complete the square on this same polynomial, but this time we'll focus a little more on the polynomial and a little less on the model. So the first thing we notice is that the leading coefficient of this polynomial is 2. We know what that means in terms of the model. It means we have 2 unit squares. In terms of completing the square, it means we're going to factor the 2 out of all of the terms in our polynomial. We do that because we want to think about what happens with 1 square only. Now let's focus on the linear coefficient. That's the 4. If we take the 4 and divide it by 2, we get 2. That 2 tells us that the length of each side of the square we're forming is x plus 2. Now we'd like to know if the polynomial we've written so far with the perfect square in it is equivalent to the original polynomial. So let's take that 2 times the quantity x plus 2 squared and rewrite it and compare it to the polynomial that we had when we factored the 2 out. Most of it looks the same. The difference is in the constant terms. Now this is the tricky part. What you have to remember is that that 2 is actually multiplying the constant term of 4 to give us a value of 8. And the original polynomial had a constant term of 6. So the original polynomial actually has a constant term that's 2 less than the one that we see when we simply have 2 times the quantity x plus 2 squared. So by completing the square, we have an expression 2 times the quantity x plus 2 squared minus 2 that's equivalent to our original expression. The models are really good at helping us visualize what's going on with completing the square, but let's try one more, and this time we won't use a model at all. The first thing we notice is that the coefficient of the squared term is not 1, so we'll have to factor that 3 out of all of the terms that we see. Our goal is to rewrite the expression so that we have a perfect square in it. And to find that missing second term in the binomial, all we have to do is look at the coefficient of the linear term, that's the 2, and divide it by 2. So 1 is the missing term in the binomial. Now the only question that remains is the expression we've written with the perfect square in it equivalent to the one we started with? So let's think about that expression, 3 times the quantity x plus 1 squared. X plus 1 squared is x squared plus 2x plus 1. If we compare that expression to the expression we had when we factored the 3 out, we can see that the only difference is in the constant terms. So how far off are we? Well, the constant term we have so far is 3 times 1, which is 3. And the constant term in our original expression was a 15. So in order to make these expressions equivalent, we'll have to add 12 to the one that we have so far. And that's it. We've completed the square when the leading coefficient is not a 1.